I'm supposed to talk about the connection between radio astronomy and cosmology. So the plan I have in this lecture is to give a kind of broad and a very brief introduction to cosmology to start with, and then take a few examples where radio astronomy has played a very important role in shaping up modern cosmology as we know. So all of you understand this part that cosmology basically refers to the study of the universe as a whole. So we are not really looking at small scales. We are looking at the universe as a whole, so the largest scales in our universe, and possibly it's one of the oldest branches of science. I mean, various civilizations have thought about it, about how our universe look like, and so on. But of course, the modern cosmology, as we know, started probably 100 years back. Uh, and it essentially started from the fact when we realized that there are galaxies beyond ours, and these distant galaxies are kind of moving away from us, which led to the concept of an expanding universe, which is now known as Hubble-Lemaitre law. Now, the the moving away of these galaxies are not random. I mean, there is a clear pattern here, in the sense that the speed of recession is exactly proportional to the distance to the galaxy. So if a galaxy is twice as far away from us, it will move away with twice the speed. And this is what gives rise to all the nice mathematical formalisms we have to study cosmology. And the expansion is characterized by what we call a scale factor, and we denote it by A of t. So it's defined in a way that A of t is 1 today in the present epoch. So clearly A would be smaller at earlier times, and A will be larger in the future. Uh, so if A is 0.5, that means the universe was kind of half the size, so to speak, compared to what it is today. Now that this expanding universe has a lot of implications, but one which is going to be very useful, and again this is something which you would have learned earlier, including in this school, is the concept of redshift. So because the universe is expanding, so is the wavelength of light, which is basically traveling through the universe, and that has been kind of indicated here. So imagine a light which was emitted when the scale factor was AEM, and it had some frequency and wavelength. By the time it is captured by an observer, the universe would have expanded. So the wavelength of the light would be larger, and hence the frequency would be smaller. So the light will shift to relatively redder wavelengths, and hence the name redshift. And in the how much the wavelength will expand will be exactly given by how much the universe has expanded, and that is essentially captured in this relation. You can see the ratio of the wavelengths observed and emitted is exactly given by the ratio of the scale factors. Okay, so if the universe has expanded by a factor of 2, the wavelength of the light will also expand by a factor of 2. And of course, the ratio of these wavelengths defines the redshift for you, which is written as Z. A observed, which is the observer, will be the scale factor corresponding to the observer will be 1, because we are mostly talking about us, we observing. And hence the redshift, you can see the 1 plus redshift factor is inverse of the scale factor. Now this is a very powerful tool, because cosmological observations let you measure the redshift of a distant object. So the moment you measure the redshift, you basically know how small the universe was compared to it is today. And this is quite profound, and that helps us gain a lot of knowledge about the cosmology, basically the properties of our universe. And as you can see, so we can relate the redshift to the scale factor. I mean, it's defined almost in that way. Now, the scale factor can be related to the time or age of the universe. For that, we have to make use of general relativity and Einstein equations and what is known as Friedman equations. But the details are not important. The scale factor is related to the time, because if we know A as a function of t, if somebody tells you what A is, you will get an idea about the time of the universe. And not only that, because we are mostly talking about light rays here, the time will immediately tell you the distance to the object, because it's the light traveling at a fixed speed. We exactly know how light travels. So in that sense, this redshift now can act as a proxy for the age of the universe as well as distance to the object. So you will hear terms like we observed an object at redshift something, redshift 2. So this is how you should interpret those statements. Okay, that's probably people are talking about how far that object is and so on and so forth. Good. Now, of course, this expansion of the universe coupled with various things we know about our universe led us to the current model of cosmology, which is the Big Bang model. Basically, at early times, the galaxies were closer to each other. So if you just go back in time, you realize that the universe would have begun from a very small region, okay, a very small size. Now, it's also well understood from basic thermodynamics that if you have some matter in a volume and if you don't let the heat escape, what will happen is as you compress that volume, the temperature of that system will increase. So using the same idea, we realize that the universe at very early times would be much hotter than what it is today. Okay, so that is something which just follows from what we know in our physics. And not only that, what we can do is we can actually work out, we can do the calculations and relate the temperature to the age of the universe. And this is how it looks like. So when the age of the universe was about a year, the temperature would be a couple of million Kelvin. When the age of the universe is of the order of a second, you can see the temperature is much higher. Okay, 10 to the 10 Kelvin and so on. So all these things can be calculated once we know the model of the universe. Now, there are very interesting things in cosmology which happens because of the expansion and the fact that it was hotter at early times. For example, if you go back early enough in time, you will realize that the universe was so hot that you could not keep electrons and protons together. So you cannot form atoms. If you try to form them, there is enough kinetic energy in the system that these two will break from each other. These will dissociate. Now you can ask then, when did the universe become cold enough so that these atoms started forming? And the answer is that the age of the universe needs to be somewhere around 400,000 years, 380 to 400,000 years. That's the time the universe is cold enough that the first atoms form. Now, what happens to the radiation is that when the atoms, when the particles, the electrons and protons were not coupled to each other, so you can think of that as a plasma, basically, a completely ionized matter, the radiation was constantly getting scattered of these charged particles. Okay? So the radiation was doing something like a random walk, which has been kind of indicated in this picture. But the moment the atoms form, the universe becomes predominantly neutral. So the radiation, the scattering of the radiation with free charges, that scattering probability goes down drastically, and the radiation essentially becomes free. From doing this random walk, it is just traveling, free streaming through the universe. Now, if this is the case, if this is what the model predicts, one can ask, can we detect this radiation? If it is free streaming, then it should be everywhere, and we should be able to detect this. And it turns out that this radiation is nothing but the cosmic microwave background, okay, the CMB. And the discovery of the CMB has a nice history, which again, many of you or all of you would know. So this was again done by Penzias and Wilson, and this has a nice radio astronomy connection, and that's why we are talking about it. So they have built basically radio instrument to study do some studies in radio astronomy and satellite communication, and they realize that they are finding an excess radio signal, which they cannot account for. What is interesting is that earlier, a team led by George Gamow had already predicted the existence of this cosmic microwave background radiation from the Big Bang model, okay, so which I was talking about in the previous slide. Now, of course, once you couple this this excess signal with this theoretical understanding, you realize that this excess signal is essentially coming from the Big Bang. Okay, this radiation which is free streaming after the atoms form. And of course, in 1978, Penzias and Wilson were awarded the Nobel Prize because of this discovery. It's so important. And I mean, it's not just the radiation. The fact that, for example, the radiation was doing a random walk. It was just scattering of these free charges before the atoms formed. It would actually achieve what we call a thermodynamic equilibrium, and hence the spectrum of that radiation will be perfect black body. So if you detect this radiation, you expect it to be a black body. This is prediction from Big Bang model. And this black body spectrum was detected in 1990s by a satellite called COBE. And this basically tries to show how perfect the fit is. So the points with error bars are the data, but the errors are kind of magnified 400 times. Otherwise, you won't be able to see them. And the black line is a black body curve. Okay? So you can see how nicely they both agree to each other. What is important for CMB is that the moment this black body radiation came, and subsequently many other observations of CMB have come, these essentially helped us discard all the competing theories of Big Bang. Okay? For example, the so-called steady state theory, which found it very difficult to explain this nice black body radiation in the universe. So once the CMB, its observations became established, we realized that Big Bang has to be the most successful model as we know, and hence all standard models of cosmology are based on this framework. Okay. Now, of course, CMB doesn't stop here. CMB, of course, if you look at the CMB, you will realize that the temperature of the CMB is essentially same in all directions once you account for the local motions and things like that. So this tells us that the universe was extremely smooth at the time the CMB originated, that is 400,000 years, when the age of the universe was 400,000 years. Just remember, the age of the universe today is approximately 14 billion years. So we are talking about a kind of baby or infant universe when we are observing the CMB. So clearly, the universe was very kind of homogeneous at very early times. But if you look at the CMB very carefully, which was done by later satellites, WMAP and Planck, you can observe, I mean, it started with COBE itself. I should also mention COBE. You observe very small fluctuations in the CMB. So it is broadly homogeneous, but there are fluctuations, and that fluctuations are tiny. Okay, we are talking about 1 part in 100,000. So 10 to the minus 5 fluctuations. Of course, the origin of the fluctuations probably have to do with some quantum effects at early time. So that's not important, but the fact is that we observe these tiny fluctuations. So they are seed of all the large scale structures we see around us today. Of course, COBE made this significant discovery. So clearly they were worthy of Nobel Prize, which happened in 2006. So basically, John Mather won the Nobel Prize for the FIRAS instrument, which showed that the microwave background radiation was black body indeed. That's very important. And George Smoot won the Nobel Prize because his instrument measured the small temperature variations of the microwave background, the small fluctuations which I was talking about. And as I said later, Planck, WMAP and Planck actually measured these fluctuations with much more accuracy and told us a lot about our universe. Of course, we see galaxies around us today. I mean, there are galaxy surveys which happen all the time, and observations of galaxies, like one which is shown here, each point is a galaxy. So observations of galaxies show us structures. The galaxies you can see are not randomly distributed. You can see there is nice structure here. I mean, there are places where there are more galaxies, and then there are voids, and then you can see things like filaments or walls, whatever you call, and so on. So, I mean, all this structure is popularly known as the cosmic web. And this essentially sets the large scale structure of the universe as we see around us today. And the reason, the origin of this large scale structure is essentially all these small fluctuations we see in the CMB. Okay, so those fluctuations grow because of gravity and give rise to these fluctuations. So that is basically what I wanted to tell about basic cosmology. And one should also end by saying that all this framework, the fact that you have CMB, small fluctuations growing, giving rise to this large scale structure, the study is known as study of physical cosmology. And physical cosmology also had a Nobel Prize in 2019. That's James Peebles who won, along with two other people who worked on exoplanets. Okay? So that's less to do with cosmology, but this one is. Now, all these observations and theoretical calculations have led to what we currently think as the standard model of cosmology. So even in the standard model of cosmology, there are things we don't understand, particularly at the very early times. But if I mean, at very early times when probably quantum gravitational effects were playing roles. Also, we don't understand the concept of baryogenesis. Why was there a small asymmetry between the number of antiparticles and particles? So yeah, but if you kind of fast forward to to about 3 minutes after the Big Bang, that is where the first nuclei formed. I didn't talk about that, but this is also something, a landmark event in our universe. So from here onwards, we think we understand the universe, or the physical processes which determine the large scale nature of the universe quite well. So 3 minutes is the nucleosynthesis. 400,000 years roughly is the formation of neutral atoms. Stars and galaxies, we have to wait for some more time before they can form. So we are talking about 100 million years or so before the first stars could have formed. And as I said, the present of the age of the universe is somewhere around 14 billion years. Okay. So this is the standard model of cosmology. Now, let's come to radio astronomy. Okay, how does radio astronomy play a role in cosmology? And actually, there's a wide variety of places where radio astronomy plays a role, and I've just picked up a few which are being listed here. This list by no means is exhaustive. So one place where it plays a role is CMB, which we talked about. Now, CMB is, of course, strictly speaking, I mean, it's microwave. M stands for microwave. So we are talking about frequencies somewhat higher than traditional radio astronomy. But if you just widen a scope a bit, you can think of CMB as something which falls under a broad umbrella of radio astronomy. But remember, we are talking about wavelengths which are somewhat, frequencies which are somewhat higher. Okay? So few tens of gigahertz to about, like, let's say about 1,000 gigahertz or so. But CMB is so important in the study of cosmology, it's often better to talk about that. So of course, within CMB, we talked about the black body nature and so on, and the fluctuations. And then there are plans to study spectral distortions from the black body spectrum, again, in somewhat lower frequencies. And these play important roles in our understanding of our universe, the formation of stars, and so on and so forth. Now, the other part which plays a big role in cosmology are radio galaxies. So these are basically galaxies which are observed in radio. And I'm sure you would have heard talks on different aspects of radio galaxies in this school itself. Now, some of the things which are which play an important role in cosmology, and I will spend some time talking about that, is, for example, the angular size versus flux relation of radio galaxies. Similarly, radio galaxies played a role in our understanding of large-scale structures through what is known as power spectrum. And then radio galaxies have also played a role in testing the concept of statistical isotropy. We think that the universe is statistically isotropic. No matter in which direction you look, the universe is statistically the same. But is it true? And some of these tests have been done using surveys of radio galaxies. Some people feel that maybe statistical isotropy is being broken, but then other people feel that there are too much systematics in the data to, I mean, one should not make such a strong claim at this stage. So jury is still out, and maybe with the future surveys and telescopes, one will get a clear answer to what this is. And then there is a field which is kind of emerging today, which is known as the 21 centimeter cosmology. So this is doing cosmology using the 21 centimeter line, which falls bang in the radio frequencies. And here there are various aspects. For example, there's the aspect of cosmic dawn and reionization, which are the effect of the first stars in the universe. And then there is a concept of intensity mapping, where you are trying to map the galaxies in a particular way. So I won't have time to talk about all these things in great detail. So I will kind of pick and choose a few and give you a flavor of how radio astronomy is shaping our understanding of cosmology. Now let's start with this angular size and flux relation of radio galaxies. This is very important, and I like it very much, because this has not only an Indian connection, this has a connection to the radio astronomy group where I work in NCRA. So think of this as, I mean, imagine a radio galaxy which is at redshift Z. So now you should be comfortable about this terminology. It's at redshift Z, means the wavelength got stretched by a factor 1 plus Z by the time it reached us. So let's say it's a faraway galaxy, and it has a luminosity capital L and some size small l. So of course, we are not going to observe the intrinsic luminosity or its intrinsic size. What we will observe is the flux. Okay, so the flux is the luminosity by 4 pi dl square, where dl is the distance. But now in cosmology, you have to be very careful while defining distances, because all these expansions and curvatures and all these things, I mean, general relativistic concepts, what happens is the distance which appears here is called the luminosity distance. So it comes with a subscript L. The observed angular size, on the other hand, which I call theta, is just L by another distance. Okay, so taking these distances to be small, you can just say the angle is just L by D. But now D is not this DL, luminosity distance. This is a different distance measure, which is called angular size distance. Of course, this luminosity distance and angular size distance are related to each other, but they are not the same. Now, suppose you take a set of galaxies, you can observe this S, the observed flux from there, and you can observe its angular size. Now, if you have a given model of radio galaxy, okay, for example, if you know how this capital L, the intrinsic luminosity, and the angular, the intrinsic size varies with redshift, what you can do is, for a given model, there will be a definite relation between this theta and this S. Now, what people did, people collected data. So these are all people from NCRA and RRI. They plotted this theta versus this flux, and you can see their data points are here. So these data, I mean, there are many galaxies, so they have just binned the galaxies, and this is some kind of median and some errors on that. Now, this is what the data says, and then they plotted on top some predictions for different models. Okay. Now, I should mention that these data points contain data from the UT radio telescope, okay, which you may have already heard about in these, like in the school. So that is why I like this application to cosmology quite a bit. So what happens is, once they plotted, so I won't have time to go into the details of how these models work, but for the moment, just take it from me that this dashed curve is a model based on Big Bang. this n equals to 0, this solid curve is a model which is based on steady state, where things are not evolving. And you can clearly see the steady state model is not at all a good fit to the data. It doesn't describe the data well at all. So these were happening in the 1970s and 80s. I took a plot from a 1987 paper, but things started in mid 70s or something like that. And that is the time people didn't know whether Big Bang is correct or steady state is correct. And there were quite a bit of discussions happening within the community. And this played a somewhat important role in actually weighing towards the Big Bang model, saying that steady state, you have to make really drastic assumptions, the evolution of the radio galaxies to make the steady state work. So this is why it's very important application in cosmology, and it's good that it came from a group in India. Of course, later, by the time Kobe went up and all these CMB observations started coming, coupled with all these large-scale structure observations, we know now that the steady-state model is not the model to describe the observations. It's the evolving Big Bang. Okay. Now let's come to large-scale structures, because if you want to apply radio galaxies to cosmology, basically you are not talking about now the properties of radio galaxies themselves. I mean, those are interesting topics by itself. But in cosmology, what is being used is the distribution of radio galaxies as a probe of large-scale structure. In this case, a concept or a quantity which plays an important role is the two-point correlation function. Now, this two-point correlation is very important in many branches of physics and astronomy, and definitely in cosmology. So basically what you are doing is, I mean, you can apply it to CMB, you can apply it to large-scale structure. The basic idea remains the same. Basically, you take 2 points separated by some distance. So if you are talking about CMB, they are separated by some angle, delta theta. If you are talking about large-scale structure, they are separated by some distance, okay, delta x. Now what you do is, you take all possible pairs which are separated by some given delta theta. Now you calculate the temperature for in the case of CMB, you calculate the temperature at these 2 points, and then just take an average of that. What you end up getting is the two-point correlation function, which now is a function of this separation. Similarly, you can do the same. Here you are not measuring temperature, but you are measuring the number or the density of galaxies, which is also shown here. So this essentially gives rise to the two-point correlation function. And if you study two-point correlation function as a function of this delta x, which is the separation, you get an idea about what are the scales where we see structures. Okay, what are the scales where structures form, and then you can couple it to your theoretical model, and you can see whether those scales are really important theoretically or not. I mean, the same information as is contained in correlation function is also contained in what is known as power spectrum. Power spectrum is nothing but the Fourier transform of correlation function. And there are advantages in using one or the other. It depends on the context. What has been plotted here is the power spectrum of density fluctuations in the universe versus K. Okay, now this K, since it's a Fourier mode, you can think of it as a wave number, and it has dimensions which is inverse of length scales. So clearly large values of K correspond to small scales, small values of K correspond to large scales. Okay. Now, what are the points with error bars are basically the measurement of this power spectrum over different observations. Okay, so for example, at large scales, you see most of the data points are coming from Planck, which is, we are talking about CMB, and then these are essentially coming from galaxy surveys and Lyman alpha forests. But don't worry about the details of these. This is what the best fit theoretical model gives. Okay? And the point I'm trying to make is the measurement of this power spectrum contains a lot of information about our universe. For example, it contains information about the primordial fluctuations, particularly the large scale version of it. And then the shape contains a lot of information about the subsequent evolution of these density fluctuations. For example, the turnover, the fact that it has a peak and it turns around, it tells us how much matter there is in the universe compared to how much radiation there is in the universe. Okay, so all these things are very important, and this is how. So the point I'm trying to make is, in large scale structure, 2-point correlation function and power spectrum are two very important quantities to study, and once we study them, we learn a lot about our universe. So the idea is now to apply the surveys in radio astronomy to try to measure this power spectrum and see whether we can learn a bit more about cosmology. Now, of course, when people went and tried to measured the fluctuations in CMB, they could also measure the power spectrum, except that power spectrum is in terms of angle. So it's called the angular power spectrum, and it shows this nice peak and trough like structures. Okay, it's clearly, it has a lot of features. And these peaks and troughs, actually, they are called acoustic peaks. And we know why they are arising. They are arising because of this tight coupling between the charged particles and the gas before the system became neutral, before the universe became neutral. And these can be calculated extremely accurately in theoretically. And you can see the theoretical model matches the observations so nicely. The red points are the observations. These are the data from Planck, and this is the best fit model we have of cosmology today. So it's remarkable. So you can see already the 2-point correlation function not only helps us in understanding, for example, the primordial fluctuation, it also tells us about how for example, the gas behaves and the radiation behaves and so on and so forth, what the state of the universe was during that time. Now, we can use this 2-point correlation to actually map out quite a bit of information of our universe. And here, radio galaxies can play a role. They haven't started playing big roles as yet compared to, let's say, the optical surveys like SDSS and BOSS, but they hold a promise in the near future. Now, of course, for the future lies in what is known as the 21 centimeter line of neutral hydrogen. And as you would have already learned, that the 21 centimeter line arises because the hydrogen ground state is split because of the interaction between the electron and the proton spin. And we are talking about two spin half systems. So it will basically get split into a triplet, which will have spin 1, and a singlet, which will have spin 0. Okay, so this is what you would have learned in your quantum mechanics. You have to do a bit more calculation in atomic physics to find out that this splitting will have a frequency difference of 1420 megahertz and a wavelength difference of 21 centimeter. The transition between these two are what we call forbidden transition. It's a magnetic dipole transition. So this doesn't happen very easily. The transition probability is really, really small. So the atom, I mean, if you want the atom in a higher level to make a spontaneous transition to a lower level, you have to wait for 10 million years. Okay? So it's really improbable. But then in astrophysical system and cosmological systems, you have so many neutral hydrogen atoms that you end up getting a signal. That signal may be weak, but you have some signal. And it has already played quite a bit of important role in astrophysics as well as cosmology. For example, the 21 centimeter emission from galaxies allowed the inference of dark matter through the rotation curve. Now, if you are planning to do cosmology, you have to do a bit more. You have to understand how we observe this 21 centimeter signal. You observe the 21 centimeter signal as a contrast with respect to the CMB. So basically what we are saying is that CMB photons are traveling from where these atoms form towards us. And if there was nothing happening, we would have just observed the CMB. Okay. But suppose in between there are neutral hydrogen atoms, what will happen is the photons which have a frequency 1420 megahertz at the place where the neutral hydrogen is, because remember, as the CMB photons are traveling, they are also getting redshifted. Their frequency and wavelengths are changing. So if they hit neutral hydrogen and if their frequency is appropriate, they will interact with the neutral hydrogen atom. They may get absorbed, they may get, there could be addition to the CMB. So what the resultant could be that we observe photons, we observe radiation, which is more or less than the CMB. It could be also same as the CMB. So a lot of it depends on the state of the neutral hydrogen when the CMB photons interact. So this is how one plans to observe the 21 centimeter signal. And this is going to be extremely important in cosmology, because since hydrogen is the most abundant element in the universe, in the large scale universe, the 21 centimeter line is kind of everywhere, and it allows us to study several aspects of cosmology and galaxy formation. Not only that, because it's a line transition, if you have access to a wide range of frequencies, you can probe a wide range of redshifts using the 21 centimeter line. For example, if you are planning to observe a nearby galaxies where the redshift will be very small, you will make observations at 1420 megahertz, or let's say 1.4 gigahertz, to observe the 21 centimeter signal. But suppose you want to observe some signal which is coming from redshift 20, extremely distant and baby universe, you will just have to tune your observations to something like 70 megahertz. Okay, so these are two examples, and you can work out what would be the observational frequency for a given redshift. Now the signal can be probed in different ways. For example, you can probe it as what we call monopole. You can just do a globally average of the signal from all directions in the sky. So it's just kind of one number per redshift. Or you can also try to probe the fluctuations in the signal. Okay, so in that case, you will be probing the spatial structures in the signal. I mean, just like what we do in CMB. So if you study the CMB as a whole, you will get this nice black body spectrum. But then you can go and also study the fluctuations in the cosmic microwave background sky. Okay? And a large number of low frequency experiments are being planned to study this universe, GMRT being one of them, and upcoming square kilometer array being another. I mentioned these two because India is part of these two experiments, but there are many others as well. Now, I will give you two examples where 21 centimeter can be very important in studying our universe. One has a concept of H1, or neutral hydrogen intensity mapping, and this actually follows from an idea by two people, Somnath Bharadwaj and Shiv Sethi, who actually gave this idea now 20 years back. Now, suppose you want to go and observe galaxies and then use those galaxies to study the large scale structure. Now, to observe those galaxies, because galaxies are, typically very small objects compared to the sky, you will need access to very high resolution. Otherwise, you won't be able to detect, resolve out each of these galaxies. But on the other hand, you also want to study a large volume of the universe because you are studying cosmology. You want to do large scale structures. So now you see this makes the whole process quite expensive because you want access to very small scales and also to the large scales at the same time. Okay, if you don't have access to the small scales, you won't be able to resolve those galaxies, identify those galaxies. Now, what these two people realize is that all these galaxies contain neutral hydrogen. Some contain more, some contain less, but they contain. And they will be giving out 21 centimeter signal. Now, what they said is that you go and try to detect this 21 centimeter signal. You don't worry about the resolution now. Just go and detect the total 21 centimeter signal. So what you will end up is with a signal which will look like this. It is low resolution, so you are not spending too much time actually trying to resolve out each individual galaxy, but you are actually trying to detect the large scale nature of the signal. So what has been plotted here is from a theoretical model, of course. These are galaxies. Each point is a galaxy, and then there is a model to populate these galaxies with neutral hydrogen. What has been plotted here is what you would have probably observed in a 21 centimeter experiment. Here you see you are not observing each point, okay, each galaxy as a point, but you are observing this neutral hydrogen coming from these galaxies. And broadly speaking, this neutral hydrogen signal is tracing the large scale structure of the galaxy. Why am I saying that? I'm saying that because look at this place. There's a lot of galaxies here, and you see there is a lot of signal coming from that place. Same here, okay? A lot of galaxies here, a lot of H1 neutral hydrogen signal here, and so on and so forth. And then there are voids. Look at this place. This is almost no galaxy. So you see almost no neutral hydrogen signal here, 21 centimeter signal here. So if you are not interested in the detailed properties of the galaxies, but just want to study the distribution of the galaxy in this large scale structure, this kind of experiments are fine. And these are, in that sense, much cheaper, so to speak. You don't really need the resolution here. You can just go and observe the large scale structure. So this is the concept of intensity mapping. And this intensity mapping has very nice applications in doing cosmology. Of course, as I said, the moment you come to cosmology and structure formation, you talk about 2-point correlation functions. So you will just go and do some 2-point correlation functions here. But of course, if you are doing radio astronomy, why do 2-point correlation function? You do power spectrum because the observations come in the Fourier space there. Okay, so the power spectrum is the most natural thing to use. And for example, of course, we haven't detected this signal directly. Till now, there have been detections using cross correlations, but we haven't detected the signal in as it is. But people have started making predictions. For example, this is a very detailed model of populating neutral hydrogen in galaxies. And what has been plotted here is same, the power spectrum as a function of K. And these are basically different models which are plotted here. And along with that, one has also plotted the noise for different telescopes, different upcoming telescopes. So this, for example, so you have to look here. So this, for example, is the noise coming from the square kilometer array. And these are predictions for different models. And you can see there are scales, which are basically scales which are here, where the signal is above the noise. So it's easy to detect them. But these are scales which are large, okay? So small k values. So this is where the intensity mapping's power can be seen. I mean, they play a big role in detecting the large scale nature of the universe. And then once you detect them, you can go and do cosmology with that. You can try to constrain cosmological parameters. You can try to study the properties of the galaxies and so on and so forth, the large scale properties of the galaxies and so on and so forth, where the intensity mapping will make a difference compared to, let's say, other optical surveys which are happening or will happen very soon, is the amount of volume probe. So what has been plotted here is the volume probe by survey by different experiments as a function of redshift. And these are different surveys or instruments in other wave bands. And this is where the intensity mapping is. And you can see it's amazing the amount of volume it probes compared to other experiments. So you can really probe very, very, very large scales in the universe. And this has very nice applications in cosmology. The other place where the 21 centimeter plays a big role is to study the properties of the first stars. Okay, so once the first stars form, the nature of the 21 centimeter signal changes. So what has been plotted here is a model, a theoretical model of the 21 centimeter signal as a function of redshift or frequency, whichever you like talk about. Okay, so, and you can see this signal, okay, when the signal is measured in such a way, is measured with respect to the CMB. So if the signal is 0, which means you are just observing the CMB and nothing else. If the signal is negative, you are observing the signal in absorption. You are receiving less radiation than what is expected from CMB. If the signal is positive, like here, you are receiving more signal than what the CMB predicts. So these are essentially interpreted as spectral distortions on top of CMB. So it's not a black body anymore. So there are small departures from the black body radiation. If it was a complete black body, the signal would be completely consistent with 0 because we have subtracted out the CMB here. And you can see now this signal has very nice features, and all these features have very nice physics inbuilt. We won't go into all the physics, but we will just focus on the most prominent part of the signal, this absorption part. And this absorption is happening because the first galaxies are forming. Okay, the moment the first galaxies form, you can see the signal starts decreasing, and this is happening because of the presence of radiation arising from the first stars. Okay, and then because you have galaxies, what happens is at some point they start heating up the gas, the intergalactic gas, and so the signal essentially starts to increase again. So this whole process of first galaxies forming and then heating up the intergalactic gas gives rise to this nice absorption feature. And a lot of instruments have been trying to detect this absorption feature, and there is a recent claim of detection which is like 2 years old already by an experiment called EDGES. So you can see the experiment is very simple here. So we're not really talking about radio arrays here. It's a simple monopole experiment. It's just trying to calculate the signal average over large portions of the sky. So they are just detecting a globally average signal. And this is what the claim, I mean, their detection is. So this is the same temperature versus redshift, and you can see they have detected absorption signal. So there have been quite a bit of controversy regarding this signal. So one doesn't know whether this signal is real or there is still some systematics in the way in the instrument works and the way they subtract foregrounds and so on. But if we take this signal to be real, we are really probing the first stars, the formation of the first stars in the universe. We are now talking about the age of the universe, somewhere around few hundred mega years. Okay, so this is, as I said, this is the time when the first stars formed. Okay, and this is something which have interested our group as well, and we have been trying to make models, and we have actually have models of the first stars. So this, for example, shows the data points, and along with our model predictions. And you can see that the model has a nice fit to the data. And this signal in our model is arising entirely because of early stars. And these stars are not like the stars you see around us today. They are much more massive and short-lived. I mean, they are basically deprived of all so-called metals. They are like hydrogen and helium-rich stars. Of course, you can go and study a bit more. You can study fluctuations in 21 centimeter. For example, if there is a galaxy, think of an idealized scenario in a galaxy forming. This galaxy will actually form 21 centimeter signal around it, and which will have very nice features. Okay, so initially it will form, I mean, around it, it will first form a blue region, which is essentially, if you look at the color bar, we are talking about negative signal, so absorption part. And then if you go far away, we will see the signal in kind of more emission. And this kind of things, fluctuating signal, is possible to observe using radio interferometric arrays. Okay, and of course, this is a theoretical model, and this is a corresponding 21 centimeter map. Okay, where the effect of the radio interferometric arrays have been put in. So you see the signal distorts, but you can still make out what the signal is. And that is, of course, the target of many upcoming experiments. And then with 21 centimeter, you can also do what is known as the epoch of reionization. What happens is, once you form the first galaxies, look at the left part first. Once you form the first galaxies, what has been plotted here is a two-dimensional slice from a model. And you are plotting the 21 centimeter signal or the amount of neutral hydrogen you have, because the 21 centimeter signal is essentially driven by the amount of neutral hydrogen. And whenever the thing becomes black, the signal is essentially going to zero. So basically, these are parts which are deprived of neutral hydrogen. And why is this happening? This is happening because the galaxies are forming here, and the galaxies are giving out radiation which is ionizing the neutral hydrogen around it. Okay, so as a result, these ionized bubbles are being formed. And as more and more galaxies form, as the universe gets evolved, what's happening is these black regions are growing, okay, growing and overlapping and merging. And there comes a time where the bulk of the universe gets reionized. Okay, so I will go back and play the same thing again. But now you can also take a look at the right-hand curve, which is plotting the power spectrum of this field. And you can see the power spectrum is also changing as there are more bubbles forming, bubbles growing, bubbles overlapping. You can see the power spectrum has some nice features. And the target of a number of radio interferometric arrays is to detect this power spectrum, and through that try to understand about these first stars. So this is another application of radio astronomy to cosmology, and that's going to play a very important role. And this just shows that there are various experiments which are trying to detect. In fact, the field was led by GMRT. The first paper came out from GMRT in 2013. But after that, there are other experiments, the MWA in Australia and LOFAR in the Netherlands and Europe. They are basically taken over the game. I mean, they're much ahead of us now. And however, I mean, these are the kind of signal, the limits they have at present. The theoretical expectation of the signal is somewhere here. So the signal is actually much lower than where the noise are. So one has to really observe for more to get rid of the noise and come to this level where one can detect the signal. And this is something which is a prime target of a number of radio telescopes. Okay. So that is essentially what I wanted to talk about. So just three main take-home points. One is that the radio astronomy has played a very important role in the development of modern cosmology. And I have talked about three main examples. One is CMB, the other is radio galaxies. Okay. The other one is the 21 centimeter radiation. And the future radio telescopes are going to have very important applications to cosmology. And just to give you a feel, I mean, this is where the current observations are. If we are talking about the signal for first stars, this is where the theoretical signal is. So we are still not there. The noise level for the square kilometer array, the upcoming telescope, is somewhere here. So you can see the moment the square kilometer array comes, the signal will be kind of extremely detectable. Okay, once we have the data analysis and other systematics under control. So this is where the future radio telescopes are going to play important role in cosmology in the near future. So that is all I wanted to talk about. Thank you very much for listening. So I don't know if there are questions, so we can take them now or.
No, sir. So I had a question about the power spectrum. So could you go to the slide where you showed the power spectrum?
Yes, let me.
No, not this one, the earlier one.
Yeah, just give me a second.
So in the near the right hand side, there is a dotted line going above the curve. So what does the dotted line represent?
Okay, so that has to do with what we call nonlinearities. So what has been plotted here is the power spectrum calculated using linear theory. Now the linear theory is what? Linear theory is when the perturbations or the fluctuations are very, very, very small. Okay, so that is where you can apply linear theory. You can ignore higher order perturbations. So in spirit, this is similar to, for example, what you do in quantum mechanics and other places where you apply perturbation theory. Now, of course, the perturbation theory the linear perturbation theory will break down as the universe evolves and you grow more and more structures, because now the perturbations have grown considerably and you have to account for higher order terms. Now, this is the prediction of the nonlinear theory in this case. Okay. Now, what you may think is that the nonlinear theory is not matching the observations. That is not true. What happens is the data points actually would, if I just take the raw data points will go and sit on the nonlinear theory in this case. Okay. What has been done is then people applied corrections to go from nonlinear to linear and brought the data points here and matched with the linear theory prediction, so that it is easy to show the results visually. When we actually make the comparisons, we actually take the data and compare with the full nonlinear theory. So it is a proper apples to apples comparison. But for visually, it's easy to see if we plot the linear theory results here. Okay, so that is basically it.
Hello, sir. I wanted to ask how like these ground-based observations, like for example, like the scar that is coming up and like the observations that have been made on the surface of the Earth are different from the observations taken from Planck, for example, like what is like the advantage that we have there, if any?
Okay. No, I mean, the targets are very different in the two cases. Planck is, first of all, it is doing at very high frequencies. So, in general, for CMB experiments, ground-based observations don't work. I mean, you know that there is a band where ground-based observations work. And the moment you are going into millimeter and sub-millimeter, that is higher frequencies, you are basically, the atmosphere plays a spoil sport, okay, because of various molecules, molecular transitions, and so on and so forth. So that's why CMB, I mean, depending on what you're trying to study, I mean, at least you have to go to balloon experiments so that you are in the kind of upper layer of the atmosphere, or you have to go to satellites. Also in CMB, the kind of experiments Planck and all others are targeting, you are basically trying to look for the whole sky, and you want to survey the whole sky in very quick time, okay, and multiple number of times, okay. So their target is different, whereas ground-based radio telescopes are talking about relatively small regions of sky, okay, but then you want to go very deep and see if you can get either the individual galaxies or the fluctuations in the signal under control, okay. So different things have different science motivations, and hence their structures and observing strategies are different.
So we're basically seeing the CMB but in different bandwidths in these different experiments.
You are okay. I mean, so if we are talking about this experiment, the 21 centimeter signal which I talked about, yes, it is like you have made an experiment to detect the CMB, and then on top of that you are trying to detect how distorted the signal is compared to CMB.
Yeah.
Okay, so you are actually observing CMB photons plus minus whatever, and that plus minus contains information about the neutral hydrogen in the universe.
So sir, like how do these future missions, even like India has one planned, CMB Bharat and all, do they somehow contribute to this, or are they just
No. So CMB Bharat and all would be at much higher. So that is more like conventional CMB. Okay.
Okay.
So that will also study, I mean, spectral distortions is one part of that, but that's a different kind of spectral distortion. And they have other things like polarization and other stuff, which are important. But that is still at higher frequencies, not in these lower frequencies. Okay. So low frequencies, it's a different game altogether. And you have to realize that the CMB is a very weak signal here.
Yeah. Okay, so thank you.
By the time there is another question, can I ask a small question, Tirth?
Yeah, Desh, please go ahead.
In your fit to the AGES result, I just missed. I was distracted during that time. What is the crucial message your fit gives?
Yes. So the model, what we have here is a population of what we call population 3 stars. That is the metal-free early stars, very massive but very short-lived. Okay. And the other thing we need to now, this is an assumption we have to put in without any real physical justification, is that these first stars are very strong kind of producers of a radio background. This radio background is needed to make this absorption dip as high as AGES probe. Okay. We didn't want to spend too much time doing a physical model is because of this controversy. So one doesn't know whether this depth is going to remain or not. But if this depth is going to remain, it's probably telling us about something additional in the universe. But the fact that the signal does this kind of behavior is essentially driven by very short-lived population 3 stars. And since this population 3 stars die, the radio background also dies, because that is another crucial ingredient to get this signal back to level 0 very quickly. So this is basically what goes as new ingredients to the conventional compared to the conventional models of galaxy formation.
I see. So it's essentially the change in the background created by the first generation of stars. Against which you see deeper absorption.
Yes, that's correct. Yes.
Yeah, okay, thanks. And what gives rise to, what was the crucial thing to make it more flat based?
So there again, what we did was we had to parameterize. So this is basically on. So we said that we don't know how the first stars formed and died. So we will take them having some predetermined parameterized form with free parameters being fitted by a statistical analysis. So this essentially is driven by the, I mean, if you look at this panel, panel B, it is the star formation rate of population 3 stars, which is shown here, the red one. And you can see this star formation, it rises at early redshift and does this funny thing, and then this goes down. There is no physical interpretation for this funny thing, doing this kind of a thing. But this is what is required to match the data. Again, we didn't spend much time thinking about the physical process because, again, we are not sure whether this flattening is real or not. But once, if you believe the data, this is what you need in the model. A star formation rate which does this kind of a thing. I don't think any physical model will give it. This is my personal feeling.
Right.
So this data has to really, I mean, hopefully it will get revised, but if it's not, we have to really think a lot.
Yeah, thanks.
Sir,
Yeah.
in the 21 centimeter map and power spectra that you showed over the evolution of the neutral hydrogen line, we see that it starts from a redshift of around 15. So what kind of telescopes and methods are allowing us to probe like the 21 centimeter line at such high redshifts?
Yeah. Okay. So first of all, this is not observation. This is a theoretical model, and the theory. So the fact that it is starting at redshift 15 is because I made a theoretical model where it starts from redshift 15. Okay. So if I had made a different kind of theoretical model, it would have started differently. However, this is a very realistic model. So redshift 15 is something. Let me just see if I have. So you see. These the current generation of radio telescopes are already probing redshift somewhere around 11 or so. Okay, so these are MWA and LOFAR. Okay, with I mean, even both of these telescopes have bands which are appropriate to probe redshift 15 without no difficulty, but there, I mean, there are other problems because of which they haven't put data up there. With SK, you can easily go up to higher redshifts, okay, because it will probe redshift 15 without any difficulty. Redshift 15 corresponds to somewhere around 90 megahertz, 90 megahertz, okay. So most of these telescopes will have bands going up to 50-60 megahertz in the low frequency range. So this is well within their reach, except the systematic challenges are much higher at those low frequencies.
Among the limits that are shown in this particular diagram,
yes.
What kind of integrations have already gone in? Of course, the systematics are doing the more nasty thing.
Yes. So the best, so these are typically few nights of observation. So one is talking about like I don't know, 40, 50 hours of integration time. Okay, so but LOFAR, for example, I know that they already have data of the order of almost touching 1,000 hours, but they are not in a position to analyze them. I mean, they are still struggling with systematics with few nights of data, as you know. So yes, so we are talking about few nights of data at this stage.
Right.
Both MWA and LOFAR.
Right, right. So Tirth, among the feasible things presently, given the technology and the other issues, practical issues, what is the most looked forward to result that in the next decade or something?
In this field, right?
Yes. Yes.
Yeah, I mean, so okay. First of all, in the global signal aspect, again, you know, I mean, one needs a confirmation of the edges signal. So one is really looking out for all the other telescopes. I mean, including the RRI group and various other collaborations which are targeting this global signal. So one needs a confirmation of that signal. And I mean, again, I'm not aware of the time scales here, but I mean, various groups are already taking the data. So probably in the next couple of years or so, we will have either a confirmation or a way to rule out this signal or some revision. So that's something one is really looking forward to, because it has kind of disrupted our like standard models of star formation and reionization and so on. In the power spectrum, the challenge is, okay, first of all, it's very difficult to understand which group is going to put out results when, because they are really, really secretive. I mean, and they have reasons to be so. This is so high stakes and so on. And what we see is a very nice competition between LOFAR and MWA in the last few years, one kind of beating the other like every year, so to speak. So in the next few years, we are probably going to see kind of incremental increase, incremental betterment of these upper limits going down. But whether we will be able to hit the point where we are able to rule out at least the very extreme models is not very clear to us, to the community. So these are the two things one is looking forward to. In the cosmology side, I mean, there's intensity mapping doing cosmology. It's slightly bleaker in that sense, because the signal is much weaker, and when one is not going to get there, where you are going to make a difference to cosmology very easily. But on the lower redshift, the advantage is you can cross correlate with other surveys. So one is also looking forward to cross-correlation studies of the intensity mapping signal with, let's say, quasars, galaxies, the Lyman alpha forest, or various other probes, which we already have. So kind of these are the three things which one is looking forward to. So let us see how things move ahead.
Yeah, thanks a lot for sharing those thoughts.